You ever stop and think about what language your computer really speaks? I'm not talking about Python or C++. I mean the fundamental, secret code that's just one tiny step away from the raw electricity pulsing through its circuits. Well, today, we're going to crack that code. We're pulling back the curtain and diving headfirst into the world of assembly language.
So, here's the plan. First, we'll talk about why on earth you'd want to speak to a computer in its native tongue. Then, we'll climb down the language ladder, get to know the CPU's personal little workspace, learn its basic moves, and then, the fun part, we'll watch a simple program run step by step.
All right, first things first, we have to understand the core problem we're trying to solve here, and that's the massive communication gap between us humans and our machines. Think about it. When you type an email or you write a line of code, you're using words, logic, stuff that makes sense to us. But a computer, it only gets one thing. On or off, ones and zeros. So how in the world do we bridge that gap? How do our complex thoughts get translated into billions of tiny electronic switches flipping inside that processor?
Well, the answer is translation. It happens through multiple layers, and you can think of it kind of like a ladder that takes us all the way from our human-friendly ideas down to the bare metal hardware. This diagram shows it perfectly. Way up at the top, you've got high-level languages like C++. They look a lot more like English, they're closer to how we think. But as you climb down that ladder, you get closer and closer to the machine. And right there, just one step from the bottom, is assembly language. It's the last human-readable stop before you hit pure machine code, the actual ones and zeros the hardware understands.
And to get down that ladder, you need special translators. For those high-level languages, you use a complex program called a compiler. But for assembly, since it's already so close to the hardware, you use a much simpler translator called an assembler. But look, all roads lead to the same place, machine code. At the end of the day, it's the only thing the processor can actually run.
So as you can probably guess, there's a big trade-off here. High-level languages are way easier for us to write, to read, to fix. But low-level languages like assembly, they are lightning fast. They're incredibly efficient because they're speaking the hardware's language. And that's exactly why they're still critical for things where every nanosecond counts, like in an operating system or a high-end video game engine.
Okay, so now let's zoom in a bit. Let's talk about where all this work actually gets done, inside the brain of the computer, the CPU. To do anything at all, the CPU needs a little spot to hold the data it's working on right now, kind of like a personal workbench. And that workbench is made up of things called registers. Now, these aren't your computer's main memory or your hard drive. No. These are tiny, super fast storage spots built directly onto the processor chip itself. It is literally the CPU's personal scratch pad for doing quick math and juggling data.
Now, what's really clever is how these registers are organized. Take the EAX register, for example. The E stands for extended, and it's 32 bits wide, but you can choose to only work with the lower 16 bits by calling it AX, and you can break that down even further into two 8-bit chunks, AH for the high part and AL for the low part. This setup gives programmers incredibly precise control over the data they're handling.
Okay, so we've got our scratch pad, the registers. Now we just need to learn the basic commands, the verbs that tell the CPU what to do with the numbers in those registers. The most fundamental, the one you'll see absolutely everywhere, is MOV. Now listen closely, because the name is a little misleading. It doesn't actually move anything. It copies. So when you see MOV AX6, think of it as copy the value 6 and paste it into the AX register. It's a copy and paste, not a cut and paste.
Next up, you've got your simple math, add and sub. And yeah, they do exactly what they sound like. If you say add BX2, the CPU takes whatever number is sitting in the BX register, adds 2 to it, and then puts the new result right back into BX, overwriting what was there before. It's that simple and direct.
And finally, for our basic set, we have JMP, which stands for jump. Now, normally, a computer just runs code one line after another, in order. JMP completely breaks that flow. It's basically a go-to command that tells the CPU, hey, stop what you're doing and immediately jump to this other part of the program. This is the key ingredient for making loops and decisions in your code. All right, the moment of truth. We've met the registers, we've learned the verbs. Let's put it all together. We are going to trace a tiny little program step by step and actually watch the data as it moves around. This is where it all clicks. Here it is. This is the entire program we're going to walk through. It looks simple, but it uses everything we just talked about. Our goal is to keep track of the values in our main registers, AX, BX, and CX,
and figure out what's left in AX at the very end.
Okay, so our program kicks off with the first instruction, move AX, 0. This is just our setup. It copies the value 0 into the AX register. At this point, we haven't touched BX or CX, so they're just question marks for now.
All right, next line. The CPU executes add AX 6. So it looks at the current value in AX, which is 0, adds 6 to it, and puts the result, which is 6, of course, right back into AX. See how it updated?
Now for the next one, MOV BX 4. Pretty straightforward. The CPU copies the value 4 into our second register, BX. Notice that AX is totally untouched during the step. It just stays at 6.
And we do the exact same thing for CX. The instruction move CX, 5 copies the number 5 into the CX register. So now all 3 of our main registers are loaded up and ready to go.
Okay, now this instruction is a little different. Add AXBX. See what's happening here? Instead of adding a plain number, we're telling the CPU to add the value from another register. So it looks inside BX, finds the number 4, and adds that to the 6 that's currently in AX. The result, 10, gets stored right back into AX.
And for our final step, the instruction is sub AX3. The CPU takes the current value in AX, which is 10, subtracts 3, and stores the final result, 7, back into AX. And that's it. The program is done, and it's left the value 7 in our main register.
Now, we just walked through 6 incredibly simple instructions, but here is the part that might just blow your mind. Every single piece of software you have ever used, your web browser, your operating system, the most complex video game, is ultimately built from millions or even billions of these tiny, logical steps, all happening at unbelievable speeds.
So it kind of leaves you with a final thought, doesn't it? Learning this stuff isn't just about computers, it's really a way of thinking. It teaches you how to take any huge, complicated problem and break it down into a sequence of small, manageable, logical steps. So what's a complex process in your world that you could start breaking down today?